Okie dokie.
Okay, so welcome to HAO Colloquium. Today, our speaker is from Cambridge, Yamini Rao. Um, Dr. Yamini Rao is a postdoctoral fellow at the Department of Applied Mathematics and Theoretical Physics, University of Cambridge, currently working on non-thermal energy studies in the chromosphere and transition region of the Sun. She is also a fellow of Royal Astronomical Society. Yamini uses spectroscopic and imaging observations from ground and space-based telescopes to probe the flows and energy from lower atmosphere to the upper atmosphere of the Sun. Her research interests are EUV spectroscopy, flows, and energy in the TR, etc. She completed her PhD in 2020 from Indian Institute of Technology, Varanasi in India, before moving to Cambridge. Her thesis topic was plasma flows and their physical implications in the solar atmosphere. Today, she will be speaking on non-thermal parametric studies in the quiet sun of the transition region. So now it's to Yamini.
Yeah, sure. Thank you, Masumi. Thanks for the nice introduction. Thank you, everyone, for coming to this talk. And so I am Dr. Yamini K. Rao, as Masumi introduced. So today I'll be talking about non-thermal parametric studies in the quiet sun of the transition region using IRIS observations mostly. So before getting into my studies, I'll just briefly explain just for the sake of the people who might not be aware of the IRIS instrument. So I'll just explain a little bit about the IRIS observations. So this is going to be the outline of my talk, where I'll briefly introduce IRIS observations and the specific spectral lines which I used for my studies to study the non-thermal velocities and why it is important to study these kind of non-thermal parameters in the quiet sun of the transition region. And then I'll also explain my another work regarding the calculation of path lengths and filling factors and the motivation behind that work. So before moving on, this is the observation from the space-based instrument interface region imaging spectrograph, which gives imaging as well as spectroscopic observations. So on the left panel, if you see, it's an image of a silicon 4 line, which has a formation temperature of 65,000 Kelvin, and it generally forms in the lower transition region. And then the IRIS also provides us the spectra, which is on the left lower panel, and where we see that two strong silicon 4 lines, which are 1394 and 1403. And then there are some faint lines as well, which are mostly oxygen lines, sulfur 4 lines, and some highly ionized iron lines as well. So on the right hand side, we see the strong silicon 1402 angstrom line, and then we have a lot of other oxygen 4 lines and sulfur 4 lines and also iron lines, and mostly these lines form at the height of chromosphere and transition region, and these are mostly the lines which I have used in my studies for different kind of density and temperature diagnostics, and then calculating the path lengths and non-thermal velocities from that. So as you can see, most of these lines are more or less optically thin lines. So they tend to show the single Gaussian behavior. So before moving on, why do we need to study the non-thermal width? So generally, any width of the Gaussian has three different has contribution from three different components. One is thermal component, another is non-thermal component, which we generally define as the excess broadening and also known as the non-thermal width. And then we have fixed instrumental broadening, which is psi I. Generally, for any line and on a particular instrument, the thermal broadening and the instrumental broadening is is a constant. So if you subtract that from the observed broadening, which is the psi, denoted by psi in this equation. Sorry, sigma in this equation. So if we subtract that, then we get this psi, which is the non-thermal velocity, which gives you the most probable velocity of random bulk plasma motions. So in this study, we mostly in this equation, we are considering assuming that all the plasma motions are Maxwellian. So there have been earlier studies where Der and Masson 1993 reported non-thermal velocities in the Quietson region using Hertz observations and found the average non-thermal velocity to be 22 kilometers per second. And then there has been a recent study by IRIS where D. Pontio et al. Studied silicon 4 line from IRIS to study different regions like Quietson active region and coronal hole, and found it to be 15 kilometers per second. They also, another highlight of the paper was to study the special resolution effect on such observations. So they used different observations at different resolutions, which is original resolution of iris, which is 0.33 arc second, and then 1 arc second, rebinning the observations to 1 arc second and 2 arc second. And they did find any effect of special resolution on these kind of calculations. So in our work, we also wanted to see if there is any temporal effect, because most of the earlier observations have used mostly carbon 4 and assume that it forms roughly at a transition region. So these are some of the previous studies which are highlighted, and what have they reported. So all these studies are nicely tabulated over here, where people have studied non-thermal velocities using silicon 4 and carbon 4 line using different instruments. But there have been some discrepancies in the earlier observations, where some people have reported root mean square velocity, some people have reported non-thermal velocities. So both the velocities generally have a factor of under root 3/2, which gets missing. So for our convenience, we have tabulated all these values according to our definition as a non-thermal velocities, and and generally the values are observed to be around 20 to 30 kilometers per second. But also all these instruments had really high exposure times, which was like of the order of 100 to 300 seconds. But since iris is capable of giving us low temporal exposure times, it was interesting to see if we see any kind of temporal effects, or if these calculations have change according to the temporal resolution. So we use silicon 4 line for calculation of non-thermal velocities, and for the sake of our calculations, we use the condition chi-square less than 5, just assuming that silicon 4 is an optically thin line and can be properly fitted with a single Gaussian, because as you see, chi-square greater than 6, so chi-square 7 and 10 10. So higher values tend to show, but it doesn't show proper fitting using single Gaussians. So we have used the condition of chi-square less than 5 for our, which does take 20 to 30% of our locations, but it at least we are sure that we are taking just the optically thin locations. So this is one of the quite thin observation from iris observed near the limb region. So if you see more on the left panel, it's a silicon 4 intensity map where we see the high intensity generally at the intergranular lanes. And then we have the Doppler velocity map in the middle panel where most of the most of the region is dominated by redshifted flows, as we generally expect in the transition region. And the Doppler velocity has a typical range of minus 30 to 30 kilometers per second. And then we have this non-thermal velocity, which is quite interesting because, as you see in this particular observation, we do have some of the limb region involved in this map. So as you go higher up radially, you see there is increase in non-thermal velocity. So there could be it might be the reason that this is the scatter plot of non-thermal velocity. And as you see that the non-thermal velocities on the disk ranges somewhere from 10 to 30 kilometer per second. But as you go just high up the one radial distance, the value shows sudden jump in a sudden jump in the non-thermal velocities, and they get shifted to values higher than 25 kilometers per second. So this is just the distribution of non-thermal velocity map, which I just showed you from for the limb region. But for this distribution, we haven't considered off the limb region. We have particularly taken just the region which is on the disk. And as we see, the peak of the non-thermal velocity peaks around 18.5 kilometers per second. And then the non-thermal velocity is well correlated with the intensity on the right panel, which has been previously observed by other instruments as well. And then we have this another observations for near the disk center, where again we see the intensity map and the red shifted dominated Doppler velocity map, and then the non-thermal velocity map, where we see that generally the higher intensity regions having intergranular lanes have higher non-thermal velocities. And if we see the distribution of this particular data set near the disk center, we see that the peak of this non-thermal velocity gets shifted to less than 15 kilometers per second. So it's somewhere around 14 kilometers per second. And then again, the non-thermal velocity is well correlated with the intensity. So we try to study these non-thermal velocity distributions for different kind of different observations, where we took 3 observations for near the limb region, and then 5 other observations from the disk. From varying from the radial distance of these observation varies from near the disk to somewhere going to up to 0.6 or not. And as you can see, all these observations have different exposures in the third column. So even the limb observations have different exposure times, and all the disk observations also have different exposure times. But that temporal exposure doesn't have any effect on the average value of the non-thermal velocities. But for the limb, its average value of the non-thermal velocity generally uh, uh, tends to show somewhere around 20 kilometers per second, while the disk observations have somewhere around average around 16 or 15 to 16 kilometers per second. So we observe that there is certain kind of center to limb variation, center to limb variation for these kind of non-thermal velocities, and such variations are generally attributed to the opacity effect. So we took the we checked the silicon 4 ratios for these two observations, and we found out that assuming that silicon 4 is optically thin line, the ratio of these two lines is values lies somewhere around 2, where the values of this ratio less than 2 shows the opacity effects, and values for these ratios greater than 2 generally shows the resonant scattering. So we see that that this effect is not due to the opacity, but it could be, but and also the fact that the non-thermal velocity values moving radially does change does suddenly change values of the disk from around 20 or 15 kilometers to 25 kilometers, does show that the plasma motions are not radially aligned but are perpendicular. So in this study we present that these non-thermal velocities have center to limb variation, which shows 20 kilometers per second an average non-thermal velocity near the limb, and 15 kilometers per second near the disk center. And these variations are also independent of the temporal exposure, where we see that iris exposure times ranging from 4 to 30 seconds doesn't have any effect. Even though Sumer earlier observations that were observed from Sumer and Hertz had really high exposure time. So it could be possible if we go really high from order of 10 seconds to hundreds of seconds, these values might show some temporal effects as well. And so we expect that these kind of motions, these kind of effects could be because of these swaying and torsional motions, which does get enhanced near the limb, and that might be the factor leading to this increase in NTVs. Although we do not rule out the possibility of other phenomena like Alphan wave may be contributing to such variations as well. So this work is already published in MNRS. So we also wanted to study these kind of then it was interesting to see these kind of variations for path lengths. So path length is one of the factors which is important to study the filling factors, which gives you which gives you the parameter of how much of mass and energy is being transferred from chromosphere to the corona. So intensity of any spectral line is generally approximated as the peak formation temperature from the contribution function multiplied by electron density square and path length. So there has been an earlier study for path length by Dare et al., where they studied Hertz observations and reported these path lengths to be varying from zero point 0.1 to 10 kilometers, and their corresponding filling factors to be ranging from 10 raised to power minus 5 to 10 raised to power minus 2. But after that, there haven't been many studies even though we have had so many high resolution instruments and observations. And also the two of the other factors were that they used the somewhere the quites near the active region. So it was mostly the Moss region where you would expect little bit higher path lengths than the quiet sun. So it was interesting to see the quiet sun observations. And then they also used the oxygen 4 and carbon 4 lines. So they use the emission measure from carbon 4 line and assume that oxygen 4 and carbon 4 lines form at the same temperature. While now with the iris, we have direct observations for oxygen 4 values. So it was interesting to see these kind of calculations from iris, directly from iris observations. So these are the oxygen 4 and sulfur 4 generally observed by iris. So as I showed you earlier, these are different oxygen 4 and sulfur 4 line, generally the sulfur 4 lines, which so mostly to study the density diagnostics, 1399 and 1401 oxygen 4 lines are used. But in our particular data set, we found that 1399 was quite noisy. So we used the blended line, which had a 1404 line, which had a contribution from oxygen 4 and sulfur 4. So then we had to subtract the contribution from sulfur 4 1406 from the 1404 line to get the oxygen 4 line, and we had to use that particular ratio. So here you see the 4 intensity maps of oxygen 4 1399 and 1401, and then we have the blended line oxygen 4 plus sulfur 4, and then the one sulfur 4 1406 ratio. So and then we have this theoretical ratio of oxygen 4, which generally ranges from 0.1 to 0.5. So but also one of the interesting addition to this work was because these are the previous observations for different quiet regions using different ratios and considering the isothermal formation temperature, different isothermal formation temperatures. And as you see, if we use, so the non-bracketed values are generally are the 1401 by 1399, and then the bracketed are the 1401 by 1404 ratio. And somewhere, if you, in some of the columns, if you see that the values are varying quite a lot by using different oxygen 4 ratios, which was interesting to see that these kind of calculation depend heavily on what line ratios you are using for calculating, because some of the values have a factor of almost 3. So you can check my paper for if you want to see more about it. But so in this particular work, we use this new Chianti atomic model by Roger Dufresne, who was a PhD student at our group and currently a postdoc. So he works on this improvisation of atomic modeling in Chianti. So on the right panel, if you see, there are contribution functions for oxygen 4, sulfur 4, and silicon 4. So the solid lines are the new atomic model, where he has taken photoionization, charge transfer, and density effects into consideration, because while the dashed lines are the zero density effects. So because these kind of processes gets dominant in the chromosphere and transition region. So it is required to use these it is required to consider these kind of atomic processes into consideration while modeling. And if you see, for oxygen 4, the peak formation temperature shifts from log T is equals to 5.2 to log T is equals to 5.1. And the peak value of the contribution function doesn't change much. But if you see for the silicon 4, which is one of the strongest line, we see that the peak of the formation temperature of the contribution function gets changed quite a lot. So it is important to use these new atomic model, which are currently not in the CAN-T 10 version, but they will get implemented in the CAN-T 11 version. And then we see these contribution functions at different pressures, and we see that these solid lines are at the ratio of this contribution function for the new atomic model, and it varies quite a lot from the old Canty model using zero density effects. So for the calculation of path lengths, we take this isothermal formation, peak formation temperature of oxygen 4 from this black solid line, which is log T is equals to 5.1. And so for our work, we also wanted to see if earlier first, and we also wanted to see some earlier observations from Sumer using these oxygen 4 ratio that we are using, oxygen 1404 by 14001. So on the left panel, we see the density using these oxygen 4 ratios, and we see that the average value of density where comes out to be somewhere around log T is equal log Ne is equals to 9.8, and there is a huge scatter, and also the path length, the average path length comes around somewhere around 10 kilometers, which is again the higher end of what Dare et al. Had reported. So, but there is a huge scatter because generally, because which has been observed in most of these, which has also been observed in a lot of earlier observations. So we calculate the path length from the disk center observations that I showed for the non-thermal velocity calculations. So we see that the oxygen 4 ratio for the particular quiet sun observation from IRIS shows that has these values ranging from zero point 0.1 to zero point 0.5, and then the corresponding density shows a typical value of 10 raised to power 10, which is generally the typical value of the density in the quiet sun of the transition region. Then we also did some temperature diagnostics using oxygen 4 by sulfur 4 ratio, which shows an average value of temperature ranging somewhere from log T is equals to 5 to 5.1. However, for the calculation of path lengths, we have taken these densities from oxygen 4 ratios from IRIS observations, and then the isothermal peak formation temperature of oxygen 4 from the Chianti improved atomic modeling, and then we calculate these path lengths. And the average value of these path lengths is somewhere around 10 kilometers, while for we conduct the similar kind of diagnostics for the limb observations as well. And these limb observations, as we see that again for the ratios lie somewhere from 0.2 to 0.5, and then we do have very less number of points as compared to the disk data set, because the data becomes quite noisy for the limb uh, for the limb region. So if you take the chi-square values, then it becomes a bit difficult to have more data points. So, and the density again shows very typical behavior of typical value of around 10 raised to power 10 centimeter cube. And then but the path length, as you see, the path lengths get shifted a little bit. So the average value of path length gets shifted to around 30 kilometers. And so There is certain kind of center to limb variation being observed even in these path length calculations from for this. So we observe these path lengths in the quiets and at the transition region, and we see certain kind of center to limb variation where the limb generally close to the limb observations had an average value of around 45 kilometers, and this center had an average value of around 30 kilometers, which is quite high than what TARE had reported. And they had reported it for around the Moss region, while we are doing it for the Quiet Sun, where we expect the rain, where we expect it to be a bit lower. But then we also calculated these pathland calculations for a lot of other data sets, and we found that these kind of calculations depend heavily on how you are calculating these pathlands. So if you are taking the direct observations or using the emission measures, so that was one of the so that is also required because the motivation behind this work was to calculate the filling factors, but then using iris we could not get the emission measure. So it would be interesting to see the emission measure from spectral lines using from the SPICE instrument, which is on board Solar Orbiter, and then taking these path lengths from the iris and combining these to see how the filling factors in the chromosphere and transition region comes out. And also it would be these kind of studies using new instruments having high resolution and temporal resolution would be used to improve the modeling and improve the modeling. So this is again one of the work that has already been published in MNRS, and I'm quite keen on using the SPICE observations for my future work. To calculate these kind of filling factors. So that's it. Thank you so much.
Thank you, Yamini. Now it's open for questions. Anyone here? Yeah, Paul.
So if we go back to the first part of your talk when you're examining the non-thermal velocities in the silicon four line.
Yeah, sure.
So you fit the line with a single Gaussian, but then throw away everything with chi-squared less than 5, right? And you
Yeah.
said that you want to do that because
Yeah.
because if it's optically thin, it should be a single that should kind of match a Gaussian profile. I'm not quite sure if I understand the reasoning there. Like for an optically thin line like silicon 4, I expect you can get a non-Gaussian profile just because of different, maybe the plasma along the line of sight has different Doppler velocities, right? So when you combine all that, it's not necessarily a Gaussian. So I'm not sure why the optical, by the opacity is your reasoning for doing that. Like this kind of ties into your finding on the non-thermal velocities being larger nearer the limb than near this center. I would expect that for the same reason, right? Near the limb, I'm looking through more of the atmosphere, so I'm summing up kind of maybe a wider range of Doppler shifts, and so we get a wider line.
Yeah, so we wanted to because we are fitting because obviously there are certain locations where silicon 4 tends to show show non-Gaussian behavior, let's say. If you see chi-square 10 does show it is not proper. If you take this location, it is definitely not properly fitted with a single Gaussian. So just to be sure that we are taking just the locations which are properly fitted with the single Gaussian. We use the chi-square less than 5, because in this, at least if you see, even chi-square is equals to 6 is quite fitted well properly with the single Gaussian. But then we found out that there were there were other locations where it wasn't fitted well, even for the chi-square is equals to 6. So just to be sure that all the profiles are being fitted properly well with the single Gaussian, we used this particular condition. So it just with the trial and error, of course.
Okay, thanks.
Yeah.
Like your example there where the chi-square equals 10, like it kind of looks like that it's not fitted well because you've got another peak like to the blue, and I don't know if that's a blended line on another line there, or is it possibly still silicon 4 but some plasma that's way blue shifted somewhere?
Yes. Yes, it could be, because I mean there are generally, I mean it also, if you see that chi-square is equals to 20, if you see there is a huge sudden, but that is just the data issue, let's say, because it just shows there is a sudden increase on the blue side, and that such kind of issues does happen in the spectral data sometimes. So we don't have any other way to deal with it.
Okay.
Hi, that was a very interesting talk. I have a question about the calculation of the non-thermal velocities. Do you use other atoms formed at similar temperatures to estimate what's the actual temperature when you were computing these non-thermal velocities?
Sorry, this?
Well, when you go into your first equation where you show how the width of the line is determined by a few different things, yes, you
Yeah.
have the mass of the atom that's down there.
Yeah.
Did you look at other atoms to confirm that this is pretty small and negligible, or used other atoms, other atomic lines?
Yeah, so we, because we are using silicon 4, so we used this thermal broadening to be thermal broadening using silicon 4, assuming silicon 4 forms at a temperature around 65,000 Kelvin. So we use that particular temperature from, and also the instrumental broadening from the D. Ponte et al. 2015. That's what they have. So we use these two values to be the fixed values that they have used just to stay consistent, let's say. And then we calculated the non-thermal velocity. Then we just subtracted those two values from the observed broadening, observed width of the Gaussian.
Okay, thank you.
Yeah.
Other questions? And online participants, please unmute and ask your question if you have. Samaya?
Hi, nice talk.
Thank you.
My question is sort of related to the Gaussians the distributions that were also not fit perfectly with the Gaussian. Some of them on double peak, for instance, that chi-square 10. Do you know where these pixels are spatially in your observations along the slit?
Yeah, so most of these, so as I told you that like this condition of chi-square less than 5 does take away 20 to 30% of the locations. And these locations mostly were into the, so these locations that we took, that is chi-square less than 5, were generally the intergranular lanes. So mostly the high intensity regions, and then these chi-square 10 or maybe the other locations which showed a bit of different behavior were mostly at the cell centers, which are generally the dark region, bit dark regions. Yeah.
Okay. Great. Thanks. Yeah, because a lot of times when I'm looking at iris data, I'm looking for those region pixels that are double peaked like that because
Yeah.
they're usually that
Yeah, so they
interesting.
were mostly in the dark region somewhere around
Yeah.
the cell centers. Yeah.
Okay, so maybe it's because of heating or some flows or some type
Yeah.
of
Yeah, it could be.
something interesting going on. Okay, great.
Yeah.
Thanks.
Thank you.
Okay, other questions? Anyone? From online, anyone? Samaya, do you have another question? Okay.
Sorry.
No, that's fine. Anyone from online or in here in the room? Okay, then let's thank our speaker again for an excellent talk.
Yeah, thank you so much. Presenting.